What easier?
Yep. It's one of those days.
Yeah, because of assignment.
Let's see. Okay. Okay, 222. Yeah. Alright, hello everybody, welcome to week 6. All 4 of us. Hooray, well 5 of us at the moment. Okay, let's just jump straight into things, I think. Let's... start that. Just all the usual stuff with Piazza and the chat in Echo 360. So that's a thing. Let's go ahead and ask a question there. Okay, so the latter part of this session today, we're going to be looking at just a bit of an opportunity to review everything that we've looked at across the last 5 weeks, because I should turn that down. It's going to be a bit of an opportunity to review everything that we've been looking at over the last 5 weeks, because because there's not actually much that we have this week, and then we're moving on to a whole other thing next week, the content for which will be up shortly later today. So without further ado, hopefully everybody's read the notes on synchronizing FSAs, so this should mostly make sense, but we're going to play around with a few examples of that, and then we will see what questions people have. So there is a post in Piazza in the live Q&A section of Piazza. If there's anything that you would like us to revisit during the latter part of today's session, please go ahead and type that in there as a follow-up discussion. And that is that. All right. Keep using the wrong mouse and keyboard. What's happening in event-driven computing at the moment? We have programming assignment 1. It's due on Friday, and I'll be adding some additional acceptance tests over the course of this week for you all to help you all out with that. But ideally, hopefully everything's going pretty well at this point, and you've got a basic test harness in place, and you've got some of the basic functionality, or most of the basic functionality, done. So really, that'll just be, triple checking that you're not doing anything horrendously wrong, as is the case with the acceptance tests, which at the moment are just making sure that your code compiles and runs. But I will be adding some additional tests that will go ahead and include things like a basic test coverage check, just to give you an indication of how well your tests are covering your code. and also a couple of basic test cases so you can make sure that your code is actually working as specified. And then it'll be a case of a combination of automated and manual marking after you've submitted and after the deadline. We'll be going through and reviewing everybody's code and getting that all sorted. Programming assignment 2, that's going to be available on Wednesday. And that's going to be about Petri nets, and yeah, should be interesting. So that's what's happening there. All right, synchronizing FSAs and review. So let's just get stuck into some examples. So the course content this week has been looking at the idea about how we can combine multiple FSAs together. Last week we looked at how we could combine multiple FSAs and perform for the purposes of concurrency. This week we were looking at it for the purposes of synchronization. And the central theme of what we've been looking at is the idea of treating FSAs as this sort of black box model where you can wire multiple inputs together. You can take multiple FSAs that behave differently to different sets of inputs, and you can effectively relabel or remap those inputs to a different set of inputs and run them simultaneously. So in this example, we have two DFAs. It's the same DFA twice. DFA 1 and 2, they both have inputs A, B, and C. We can see the transition table up there in the top left for the DFA, and we can see over on the right here, if we treat them as a sort of black box system, how we might wire them together with this new set of inputs, which we're calling Q, R, S, and T. And we can see how those new inputs map to each of the inputs on the individual DFAs in this combined system. All right, let's take a look at what this actually looks like for us. So we have usual thing with the document camera. How blurry is it? Let's find out. Okay. Oh, that's pretty good. Okay. So I think one of the first things that might help is if we go ahead and if we draw out this DFA. So we have three states, Q1, Q2, and Q3, and three inputs, A, B, and C. And I'm going to draw two of them so that we can sort of map out what everything's doing. So we know that both these systems start in state Q1. And let's take a look at what we've got. We have A goes to Q2, B goes to Q3. And in Q2 we have B goes to Q3, C goes to Q1. And in Q3 we have C goes to Q1. Okay, and we're going to have two of those. Okay, so same DFA twice. Move that down a little bit. Okay, and then the question is, when we wire it up in the way that we have in the diagram, which I'll just switch back to here. So we have on the, what will make the top one, we have A, B, and C maps to Q, R, and S in this way, and in the bottom one, DFA2, we have Q, T, and S being mapped in according to this black box diagram. So how do we go about implementing this system? Well, let's first take a quick look at how that's actually going to play out in terms of how everything runs. So you'll be switching back and forth. All right, how's this system initialize? What states do we initialize into?
Q0. Is that?
Is there a Q0?
I can see Q0. Isn't it the first one is Q0? Oh, it's a Q1, Q2, Q3.
Sorry, yeah, that's a bit of a rubbish one. Yeah.
Q1.
Yeah, so we're going to initialize into Q1 on both of these.
Sorry,
Yeah,
I'm sorry
exactly.
for seeing the same Q0 everywhere.
Seen Q0 every week, and then we've got Q1 this week. Yeah. Okay, yeah, so it's Q1, Q2, and Q3. We initialize into Q1 like so. And so all we really need to do to map this thing out is we want to draw a transition table for this new system, and then in the same way that we map an NFA to a DFA, we map these two DFAs out into a new DFA. Which kind of makes sense, right? Because if we consider this to be one system, what type of FSA are we looking at here? Like, if we pretend for a moment that we're not looking at two separate DFAs, but we're looking at one whole system here, by definition, what type of system are we looking at? Come on, people watching at home, I see the 5 of you there. I see the chat. What type of system are we looking at?
Something which is synchronizing and giving us a new output.
Yep, yeah. We're aiming to synchronize these systems and get a new output. That's the goal. But what does this look like?
It could be 2 gates.
Could be 2 gates. Yeah, potentially.
Yeah. So one is opening, other one is like probably closed.
Mm-hmm.
So we know one way is open, other one is not.
In like the theoretical context of the systems that we've been looking at so far, does this look familiar, or does this look like anything that we've already seen?
You mean by technical term?
Sure.
To be honest, I haven't studied for this actually because I was so busy on assignment.
Does it look like anything that we've seen in previous weeks?
Would you give me some hint? Like
Well, it kind of looks to me like an FSA, but it's just like split into 2 separate FSAs, which, that's effectively what it is. But if I was treating this as like one system, what definition would this fall under? Like, this can't be a DFA.
Yeah.
Right, it can't be a DFA because we're in 2 states simultaneously.
I can guess, but I'm thinking why I guess it, and you ask me, I'll say it, and I'll be like, I'm guessing. I can't say that. Say, it looks like an NFA.
Yeah, it looks like an NFA to me as well. It's like it's disjoint.
Yeah.
There's like 2 separate parts to it, but there's no epsilons in here, so this can't be an epsilon NFA. But we're in 2 states simultaneously. We initialize into 2 states at the same time.
It's an NFA.
Yeah.
That's a good enough reason to say that it's an NFA.
Yeah, pretty much. Because there was no point where we said that the NFAs that we were looking at before, like when we were looking at the NFA for like, oh, is it the word hello or is it the word hi? There was like the examples that we've seen have all sort of had everything together as one system, but there's nothing to stop us just making it 2 separate disjoint systems that are initialized. Well, that's the same system, but it's one NFA, but it consists of several disjoint components, and that's effectively what we have here. Now, there's one thing to bear in mind that the notes do flag on this, and I think there's a reasonable argument to be made either way. The notes suggest that when one system ceases to function, that we consider the whole system to be ceased to function in this type of setup here. I think there's a reasonable argument to be made either way. If you consider this to be an NFA, by the definition of an NFA, the system only ceases to function when when both have stopped working. However, because we are mapping these to a new set of inputs, there's a reasonable argument to be made as well that because we can't, if this system were to cease functioning and die because we got, maybe we were in, I don't know, state Q3 and we received an A as an input, and it's like, okay, well that doesn't go to anything, so that stops. There's a reasonable argument to be made that, okay, well, we can't really map input P, or whichever input it was it input P? Q, it was input Q. We can't really map input Q to anything on the bottom system because the bottom system is no longer functioning. So we say at that point that, okay, the system as a whole has ceased to function. So that's something to be aware of in the way that these systems have been defined in the course notes. So if one system dies, we consider the whole system to cease to function. Otherwise, it just sort of flails around doing nothing.
Question, I do understand what you're trying to tell us, but our question is like, why are we having two DFAs where we can have one NFA? And we can say NFA is like connecting to this DFA, which is basically gonna be one NFA. And if it dies, then I got other things, like other scenarios to be running at the same time. And I can say, yeah, I don't need a two DFAs to combine it. I can simply just go with NFA.
Oh, I mean, the point is that I think the point that we're getting at with these systems is that you can combine multiple simple disjoint systems together arbitrarily to make something that is more complex as a whole. So in this case, we were mapping, what did we end up with? We ended up with, we had Q maps to an A on the top machine and an A on the bottom machine. We had a R maps to a B on the top machine only, but doesn't actually input to the bottom machine. So the bottom machine, like an input comes into the system as a whole, but it doesn't affect the bottom machine in that instance. An S is a C, no, sorry, it was an A and a C. So this was A and a C, an S was a C and an A, and a T was a B on the bottom machine, and nothing on the top machine. So that's the setup that we're looking at there. Yeah. All right, so now that we have this, all we have to do is draw up a new transition table for this new set of inputs that gets mapped to our existing sets of inputs on both machines, and then we play the system out just like we would with any NFA, because this is effectively an NFA as we've established. So, yep, let's draw this a little bit lower. I started with P, didn't I? Q. It's okay, this is why we have multiple sheets of paper. Okay, QRST. There we go. And the system initializes into state Q1 on the top machine, Q1 on the bottom machine, which I will refer to as Q1, Q1. Q1, Q1. And then we just play out each of these inputs on the system and we see where we end up. So if we are in state Q1 on the top machine and we receive an A matching with this Q, or if we receive a Q which maps to an A, where does that put us?
Q2.
Yep, that puts us into Q2. And if we are in, if we receive a C on this one, where does that put us?
Q1 back to it.
Let me just double check the transition table to make sure I'm not messing this up, but we are in state Q1 and we receive a C, system ceases to function because there's no outbound C from Q1. So we can just say that Q doesn't do anything for us. Let's reset the system. We're in state Q1, Q1. We receive a B on the first machine. Where does that put us?
Q3.
Yep, so that puts us to Q3 here, and it's a B on the top machine, it's nothing on the bottom machine, so we don't actually send an input to the bottom machine doesn't change state. So we end up in state Q3, Q1. Okay, let's put that as a new state and reset. Let's take a look at S. If we receive a C on the top machine and an A on the bottom machine, well, that's the reverse of what we had in the first case, so we know that that didn't do anything for us. And finally, if we receive a B on the bottom machine, that's going to put us into Q3 down here with a T, nothing on the top machine, B on the bottom machine, so that's going to give us Q1, Q3. All right, and we move on to the next state, and we just build this thing out. So we're in state Q3, Q1. If we receive an A on the top machine, that's going to do nothing for us, so we can just stop right there. If we receive a B on the top machine, again, that's going to do nothing for us. If we receive a C on the top machine and an A on the bottom machine, so a C on the top machine puts us here, A on the bottom machine puts us there. So that's going to give us Q1, Q2. Okay, Q1, Q2. And so we were in Q3, Q1. And finally a T, which is just a B on the bottom machine, is going to put us there. So that's going to put us in Q3, Q3. Yeah, not as much as you'd think. In theory, the maximum number of, well, in theory, what is the maximum number of states that we can have in this system? In this system.
Will be, I'm guessing, 6. Yeah, 6 maybe.
6.
Isn't it transition sigma and transition equals to total number of transitions? I read somewhere, sorry.
It's okay. It's going to be 9 in this case.
9?
Yeah. So it's because there are 3 states in the top, 3 states in the bottom. So 3 times 3. Yeah. So because Q1, 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 Q2, Q1, Q3. Q2, Q1, Q2, 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 and so on and so forth. And it's like those are the only possible set that we can have. So at most we're going to have 9 distinct states in this system. As we've already seen, well, as we're probably going to see, we're going to end up with less. There are going to be some that just are not going to be reachable, which is why when you're mapping out an NFA to a DFA, some people like to start by just like listing all of the possible states and then trying to like map them all out, and you realize that there are entire sets that are unreachable, which is why we always build out from the start, because I don't know, but, yeah, saves time. And oh, I forgot Q1, Q2. Okay, so saves time, and you know, we might finish here. If this is the initial state, we might finish at this point. We'll find out. All right, so we need to do Q1, Q3, Q1 here, Q3 here. If we receive an A on the top machine and a C on the bottom machine, that's going to put us into Q3, Q1, which was that state there, which we've already had. All right, if we get a B on the top machine, that's going to put us into Q3, Q3. Okay, if we get a C on the top machine, okay, well that's going to do nothing for us. And if we get a B on the bottom machine, that's going to do nothing for us. Both of these states already existed. This one's here and this one is here, so that's doing okay. Let's put us into Q3, Q3. All right, if we get, now I think we're probably already seeing that both of these are going to not work for us, because in either case it's going to put an A in one of these, which neither of them has an outbound A. Do we have any Bs? No. So I think we're actually reach a deadlock at this point. And Q1, Q2 over here. And if we receive an A on the top machine, C on the bottom machine, then that's going to put us into Q2, Q1. So, okay, if we receive a B on the top machine, that's going to put us into Q3, Q2. So, if we receive a C on the top machine, that's going to do nothing for us. And if we receive a B on the bottom machine, that's going to put us into Q1, Q3. Okay, Q3, Q2 is a new state. Let's take a look, and we're going to look at Q2, Q1 now. All right, same deal as before. I think this works pretty much the same as this one, but these two are swapped around. Except this is going to be Q. Did I? Hang on, did I mess this up? Yeah, so no, that is going to be Q3, Q1 here, which we have here. An S is going to be a B in the bottom system, which, sorry, an S is going to be C in the top system, A in the bottom system, so Q1, Q2. And the last one is going to be a B in the bottom system, which puts us into Q2, Q3. And is that new? I think that is new. Did we actually end up with 9 states? 1, 2, 3. I think we've got everything except Q2, Q2 here. Again, but we're not necessarily going to ever hit Q2, Q2, so let's put us into Q3, Q2. And let's keep going. So we have A in the top machine. Well, that's going to break that. B in the top machine only is going to break that. A in the bottom machine is going to break. And B in the bottom machine is going to put us into Q3, Q3, like so. And that just leaves Q2, Q3, which is going to be the same as Q3, Q2, only backwards. So that's going to put us in like so. And that's our transition table for the DFA resulting from combining these two systems or synchronizing these two systems, mapping QR, S and T to A, B and C according to that diagram.
I think there is a mistake.
You think there's a mistake?
Yeah.
Where did I mess up?
100%.
No, I make mistakes all the time.
So it's the second last line
Mhm.
on the
Okay, so we
second last line.
put us into Q3, Q2.
Which is S. We are looking for S.
Ooh, S.
Q3, Q2, S. Yeah. So SA is from Q3, it goes to Q1. SC.
So on this system, Q3 would go back to Q1
Yep.
on the top,
Yep.
but on this one, there is no outbound A from Q2. So the system dies at this point.
Yep.
Yeah,
So thanks.
that's all good. So we could rename all of these states if we wanted to. Let's just call them, I don't know. I'm going to call them N1, N2. Going to rename these states, and we can then draw this thing out if we want to as a new system. And then we just have to, map each of these out to their corresponding things. So Q3, Q1 is N2, so
Which one gonna be a final state? May I ask this question?
well, this system didn't have a final or accepting state. So arguably this sort of thing,
It depends on the regex, like what we are passing.
well, it depends on the systems that we're dealing with input wise, because there are kind of two separate use cases that we can consider for using DFAs or FSAs in the way that we have been. There's the type of system where we are running through a set of states and just going from state to state to state to state until we are in an accepting state, and we want to know, okay, are we in an acceptable place after a sequence of inputs? That can be very useful in things like safety control systems, where you want to go, okay, well, is it safe to shut the system off or something like that? If I do this sequence of inputs, is everything okay for me to, proceed and press the big green button or something like that, or, shut the system down or whatnot. So we have that kind of system, and as we've seen, it's also useful for string processing. We can take a regular expression, run it through a DFA, and we sort of get this, okay, did it match or did it not after a certain sequence of inputs? That's the case where we have an accepting state, but we also have like another set, or we also have DFAs where maybe we're trying to represent some of the systems that we've already looked at with our million more machines, for instance, where you have things like, okay, well, a garage door system where the system is going to run continuously. There's no accepting state because the system doesn't ever stop as it was. We don't ever need to check, is the system in an acceptable state? We just need to make sure that we have, that we know which state we're in at any given time. So in this case, this represents one of those, because this kind of use case is good for synchronizing multiple distinct systems of that type together. So maybe you want to synchronize your garage door with, I don't know, your home security system or something like that. So you want to map out, okay, well, if I connect up my two controllers together, if I connect the garage door controller, which has this set of inputs, and I connect the security system, which has this other set of inputs, to like the same controller, and I map them together so that, when the garage door is closed and my security system is armed, then, do this, versus when the garage door is open, we don't necessarily want the security system to be armed because I've explicitly left the garage door open, that sort of thing. Why we're talking about garage doors and security systems specifically, don't know, but that's...
That was a good example.
Yeah. So that's kind of what we're aiming for with this whole synchronization thing. Theoretically, there's nothing to stop us from from having accepting states in here. And if we did want to have accepting states, actually this follows on a little bit. We can come back to part 2. It was just another example for part 2. No, this follows on nicely to this discussion. So, as we've already talked about, does this work with NFAs? And we kind of said, well, in theory, there's nothing to say that this shouldn't work with NFAs. We just need to be aware that when we're synchronizing systems like this, the basic rules, one of the basic rules that we have is that if either of the systems breaks, we consider the system as a whole to be broken. So if one system stops, we say the whole system stops. Could we do this with NFAs? We've already established that this is effectively what we're looking at is basically an NFA as it is. It's disjoint, but we have these two separate, we have effectively one system which has two states. And even though these aren't connected, all this is okay, we're in two states simultaneously now. This is an NFA. It's like, okay, well, that's nice. So could we do this with NFAs? Yes. There's no reason why we couldn't do this with NFAs. There's no reason why we couldn't do this with epsilon NFAs. We just need to think about what desired behavior. When we start getting more non-deterministic with this, we need to think about what desired behavior we should have when one of the systems ceases to function. We've said that if one system ceases to function, then the system as a whole ceases to function, but that is that's effectively working off an assumption that both of these systems are important independently, and therefore if one system stops, we should consider the whole combined system to be null and void at that point. Maybe there's a scenario where it actually makes sense for you to have multiple disjoint systems that you connect together in this fashion with this new set of inputs, where it doesn't matter if one system stops or not. So yeah, it could be context dependent. We're working on the assumption that if one stops, the whole system stops. Well, okay, that actually pretty much covers everything there. Could we do this with... Any additional thoughts or questions on the synchronizing stuff? We'll go back and do another example in a moment, but... Sorry?
Actually clears everything.
Okay, that's good. We won't do this next example in full, but we included this one just to point out they don't have to be the same DFA. Like in the previous example, it was the same DFA twice. Here we have two completely different DFAs that we are wiring up in a similar fashion. So I'm going to leave this on the screen and draw up a couple basic diagrams very quickly and then switch over. So what have we got? We have 3 states in the first one. Oh, that's convenient. They've labeled the states differently, so that's all nice. Let's see. So we have S1, S2, S3, and we have S4 and S5, and so we have okay, that makes sense, and in the top one A, B, and okay, and if we're in S2, then okay, and B and C both go to S3, and if we're in S3, B goes to S2, C goes to S1. And okay, so it's going to look something like this. All right, maximum number of distinct states that we could end up with in this system.
Oh, maximum.
Yeah.
Well, yeah, 3 to 5. It's just solid.
So good. Maximum number of states that we could potentially have out of this system? 6, yeah. 3 times 2. Yeah. All right. Initialize the system to S1, S4. Wait, is S2 the initial state in the first system? Okay, so we initialize in S1, S4. Yep. Cool. That's good. All right, and then what's our, I'm going to keep going back and forth, what's our mapping? So we have P is A plus X, R is C plus Y, so P is A and X, Q is B, and R is C and Y. Yep, okay. That seems good. All right, so okay, so first system A and X would give us this. So this is S2, S5. So that's P. Okay, let's take a quick look at Q. Q is B on the top system. That's just going to leave us in the same state. S1, S4. And R is C and Y, which is going to break the bottom machine. So that leaves us there. Let's try S2, S5. Okay, and A on the top machine, there is no, oh no, it's S2, and X is S5, so we stay where we are. And with a Q, that's B on the top machine, so that's going to give us S3, S5. And R is going to give us a C on the top machine and a Y on the bottom machine, so that's going to give us S3, S4. And okay, S3, S5, let's map that one out. Okay, A on the top machine doesn't give us any. Did I map that right? Did I miss something? No, that's literally the only case. Okay. And that's going to be the same for S3, S4 because A on the top machine in either case isn't going to help us out. All right, B on the top machine is going to move us back to S2, S5. And C on the top machine and Y on the bottom machine is going to put us into S1, S4, which is the initial state. So we have no new states here. Let's take a look at S3, S4. A B on the top machine is going to move us to S2, S4. Did I miss one here? Hang on. Ah, right, okay, all right, so that's S2, S4. And R is going to be, what is it going to be, people? And there's no Y from here. So this one's going to die. Yep. S2, S4. Okay, S2 and S4. With a P, that's going to be A and X. So that's S2, S5, which we already have. And with a Q, that's going to be a B. So S3, S4, which we already have. And C on the top, Y on the bottom is going to give us, again, the X on the, or the Y on the bottom, which doesn't take us anywhere. So that leaves us there. So we've ended up with only 5 states. That's this system. And we can map that one out in the usual way. And that's pretty much it for examples. We can draw this out, and we can rename and remap them and draw it out as DFA if we want, or as we please there. Any general questions that we want to ask about any of the synchronization stuff? And that goes for people watching at home. Again, if you have any questions, you can ask them in Piazza or in the Echo 360 live chat.
So which state we miss? I mean, we don't need.
It's going to be S1, S5, I think. So if we initialize the system here, we would need just an X and nothing, or if we were to, so that takes us to S2, S5, we would need a way to somehow get back, so we would need a B here, which would take us over to there, that would be a Q, but then to get back up to S1, we would need an R from there, and that would flip us back over to here, so we never actually end up with S1, S5 in the system. Again, a good reason why we want to map this out from the starting state rather than just go, oh, well, there's going to be 6 states, and just write out all 6 states and then try to fill out the table. I have seen people get like pro tip for the exam, because you will probably get a question like this about this in an exam. I have seen people with a 4x3 table, so it's 12 possible states, try to like map out all 12 states. They like write out the entire set of 12 states, and then they just fill in the line for each one. And the system like only had maybe about 5 actual reachable states in it. So they ended up with like this disjoint system and an entire chunk that was just entirely unusable and unreachable.
So we always start from the initial state.
Always start from the initial state and map it out, yeah. And that goes for, I think, can't remember whether it was one of these or whether it was like an NFA conversion or something like that. It got messy. It was like, they were like, oh, why was the exam so long? I was like, it wasn't meant to be this long. Anyway, that's a bit of a sidetrack. So that's all of that. Does anyone have any questions about anything that we've covered up to this point, including but not limited to NFAs, epsilon NFAs, stuff for the assignment, Petri nets, yeah. And it goes for your watching at home as well. I'm watching this Piazza. I'm not seeing anything on there yet.
Yeah, I've read notes about epsilon NFAs.
Mm.
Yeah. I'm a little bit confused what actually can an epsilon, I mean,
Can you?
yeah, this input can use with.
Yeah, that's fair. Epsilon is a little bit confusing like that. So the question was like, okay, but what actually even is an epsilon? Epsilon isn't an input. It's this representation of the idea that we could take an input if we wanted to. I think rather than trying to understand what epsilon represents in like a theoretical sense, the way that I like to think about epsilon is with a practical example. And so if I have a regular expression A star or B, now wait, let's document camera. Let's say I have A star or B. Right, and we know that this represents like either some sequence of A's or just B by itself. How would we draw this as a DFA? So without the epsilons, how would we draw this as a DFA? Let's initialize here's our initial state here. So what are our options? It's any number of A's. Yeah.
Without, it's kind of tricky. I think we can't do it. Can we?
We can. So the answer is we can, but it's a little bit tricky because your immediate like the thing that I immediately want to do when I'm presented with this problem is just like, oh, A star. Okay, well this is A star. Like, okay, cool. There's A star. It's just like A star or B, and it's like, oh, okay. Well, you can do that, or you can do that, and then you realize that this would also accept like that, which is not acceptable in this NFA. So we need some way of like having this loop with the A's, and also accepting the B's without actually like allowing us to go back. So if we represent this as an epsilon NFA, and like I mean, how would we actually answer this? The way that we would actually answer this is it would be, you know, a double circle like that, and then an A over to here, which is also an accepting state, and then an A like that, and then a B like that. So nothing is acceptable, or at least one A, or multiple A's. So this effectively then becomes a representation of nothing or A plus or B as what that represents. So that would be like the correct way that you would do it with a DFA, but it's really tempting just to start here, and a lot of people will make this mistake. So the idea with an epsilon is that you can have your initial state and we can have like this.
But it's
And by adding these epsilons in here, you can't go back. The arrow only goes in the one direction. So it represents the idea that it's just like, okay, well, if we wanted to go down this pathway, we could, or we could go down this pathway, but we still start off here.
but it's still an NFA, right?
Well, this is an epsilon NFA. If we wanted to represent this as a regular NFA to start with, we could take a more simple approach to this as a regular NFA would be to have it as a disjoint NFA. So we could have like this, where you have it's two separate NFA. Well, it's two separate. It's effectively two separate DFAs, but it is an NFA because, you know, they are connected to each other. Well, it is part of one system, but you initialize into two states simultaneously, and these are completely disjoint from each other. So if I get a B, this part stops working, and I end up here in this accepting state. If I get any number of A's, then this part stops working, but these parts stay active. And if I get anything else, both parts stop. So that's how you would do it with a regular NFA. But if you start to get like more complicated expressions, or you're trying to represent it as a single connected system, that's where things start falling apart a little bit. So that's why we have the epsilons as a tool for us to use.
Okay.
Yeah.
So it's kind of loose.
Make things simple.
Yeah, it's effectively a way to loosely couple these together. Yeah, that's a good way of putting it. Yeah. Anybody at home, do you have any questions that you want to ask? Still very quiet in the piazza and in the chat at the moment. Yeah. Yeah, absolutely.
Okay, so basically we only require 4 rows of that, right? The star, the alternation operator, class operator, and brackets.
Yep. Yep. And I'm not going to require you to figure out how to deal with nested brackets. But you will still have to do like a little bit of figuring that out depending on order of operations. But I'm not going to require you to like go 10 layers deep with brackets or anything like that.
So about the inputs, I mean the test file, right? We are given the test file by ourselves.
Yeah, you're going to need to come up with your own test cases. And the inputs can be any characters that are, well, I mean, I'm probably going to restrict it to, you know, the numbers. Actually, I think I said on the assignment what it would be, but I think I said numbers 0 to 9, letters A to Z, upper and lower case as the possible options, and also spaces. You don't need to worry about different types of white space. I will restrict it to like actual spaces. But for the most part, I will probably try to stick to just regular letters. But it's not just going to be A, B, and C. It's going to be, you might have some X's and some 3's and various different bits and pieces in there.
So it sounds like a really stupid question, but still I'm gonna just.
There are no stupid questions.
So we have 2 parts in assignment 1, yeah. The first part is basically checking the regular expression and passing input, issuing, whether they are matching or not. Yeah, for example, the regular expression is in bracket AB, colon, do we pronounce as a colon, or star,
Clean star.
or C+, yeah.
Okay.
Then we have to write a program which can check whether the passing in string, for example, ABC, is true or false. Yeah.
Wait, sorry, what was the first part again?
So we'll get two inputs from user. The first one gonna be regex, which is like AB bracket
Yep.
or C+, and then user gonna pass string.
Right. Yep.
Yeah.
Yeah.
And then we just simply have to check whether it's true or false.
Yeah. That's pretty much it. Yeah, there are two distinct parts to handling the user input. There's the part where there's the very first part, which is where you're given the user provides a regular expression, and then it's your job to parse that regular expression, convert it into an epsilon NFA representation, and like build that up so that you can actually evaluate it. And then the second part is you read the user inputs provided and you evaluate the epsilon NFA against those user inputs to determine if the strings themselves match the regular expression or not.
That was the confusing part for me. So the first part I actually thought is a regular expression passing in. You have to check it whether it's correct or not, and then answer it like through it, output true or false.
I mean, that's what the program's input and output represents, yes.
And then second part was, I was thinking is like using epsilon NFA to make a transition table and then evaluate at the end, give a result while showing transition table.
Yeah.
So did I understand correctly these two parts?
I think so. I mean, the important part is that you are actually using an epsilon NFA to evaluate your system. Whether you're down converting the epsilon NFA into a DFA when you actually perform your evaluation, or whether you are evaluating on the fly, that is the important part with this assignment. And if you're not doing that, then your marks are going to reflect the fact that you've been asked explicitly to do that and then you've just not done that.
So what we should write about the code is basically we use epsilon NFA, convert to a DFA.
May I?
You don't have to convert it to a DFA. Like we've talked about it in terms of converting to a DFA because we aim to get as much simplicity and determinism into the system as we can. But as you're probably aware, the actual steps to performing the conversion, it's like a fixed algorithm that we do effectively. We say, okay, initialize the system, then, depending on which approach we're taking, greedy or lazy, are we, evaluating the epsilon transitions to get the epsilon closure, then we evaluate an input against the epsilon closure, or depending on which approach we have. And then it's like, okay, well, that's the new set of states that we're in. And then it's like, okay, well, that's a set of states. And then we can use those sets of states effectively to remove all the epsilons out of the system and end up with an NFA. And then we can down convert that to a DFA. But we don't necessarily have to do that. We can just play out the epsilon NFA and see if we hit an accepting state at any point in time. We just have to be aware of which approach you're using, whether you're using the greedy approach or the lazy approach. Because if you're using the lazy approach, then you have to be careful, because the accepting states in the lazy approach, you have to sort of make sure that you evaluate them into all the other states based on the epsilon closure. Like in the lazy approach, all of your finishing states end up as states whose epsilon closure contains an accepting state. So you need to remember to evaluate that into your system if you're taking the lazy approach. If you're taking the greedy approach, that happens automatically, but you do need to remember to evaluate the epsilon closure initially at the start. Otherwise, you'll be out of step.
So the verbose mode, the output, the second output, so is the transition table we had to map out as the input, as given the input.
Output. As an output.
Yeah, we need to make sure there's a transition table can be as an output.
Yeah, yeah.
verbose mode.
Yeah, so for verbose mode, the epsilon NFA that you generate from your regular expression, I'm asking you to spit out a transition table for the epsilon NFA that you've generated. I don't know why I added the other column at the end there. There really is no need to have the other column as the last column that you'll see in the example output. There's like epsilon, and then there's all of the different inputs that appear in the table, and there's an other column, and I realized afterwards that there was no need to have that there, but
I would really recommend you write down this on Piazza, because to be honest, I wasted my one day of trying to look for the relations on input. And then I was reading carefully because I knew that I was missing something there. And then I realized that, oh, okay, epsilon table, transition table, this is just an example. It can look like a bit different. I was like, okay, damn.
yeah.
I was like,
Yeah, there is an actual, I'd have to, I can draw it up for you. I can draw up the epsilon NFA that transition table represents, and that is an actual epsilon that example does actually work. But that just is the epsilon NFA that I came up with by manually drawing it out. And your epsilon NFA may have a whole bunch of extra states and other stuff in it, depending.
Is it all right, like as long as it's understandable and we are using epsilon NFA way?
Yep.
And making epsilon NFA transition table, then converting to the FA. This should be all right if I'm like outputting a whole bunch of transition, how my program did it. Is this still gonna work? All you wanna see is like transition table of ENFA. It might be not really understandable.
Yeah, I mean, I'm going to attempt to automatically evaluate your transition table. Depending on how I go with that, that could be a bit of a challenge. And a question has just popped up. If we cannot print out the transition table in the verbose mode, how would that affect our grade? It depends on whether your system is actually generating an epsilon NFA or not. Because if you are generating an epsilon NFA and you're just not printing it out in the transition table, from my perspective, that's still deserving of most of the marks. But if you're, for want of a better term, if you're half-assing this assignment and you're just going, oh, okay, I can sort of just throw some code together to deal with each component or part of a regular expression. That's not what we're aiming for here. The whole point of this course is to look at different approaches to handling event-driven systems. And this assignment is focused on using epsilon NFAs to evaluate regular expressions. So if you are not using an epsilon NFA to evaluate your regular expressions, then as far as I'm concerned, you have not satisfactorily completed the assignment, and your mark will reflect that. So if you don't get the transition table in there, oh, look, it's not the best, because it's gonna, like, from my perspective, I'm gonna have to put some extra work into the marking, but I'm not hugely fussed about having to put some extra work into the marking. If this was a class of like 300 students, that might be a different answer. But for the 50 of you that there are, I'm okay with putting in the extra work on marking. You won't get the full marks, but you will still get most of the marks, provided that the rest of the code is actually generating an epsilon NFA and using the epsilon NFA to evaluate it.
So the core is that we have to use the epsilon NFA to passing inputs into actually a string or a transition table.
Yeah. So, well, I mean, okay. So here's our epsilon NFA just here in theory. Or if I were to take a more procedural approach to generating this, here's what I would probably end up with. So if we had A star or B, right? So one of the challenges for you all to work out is how to deal with the order of operations. But once you've got the order of operations figured out of this system, for me, I would be translating this into something that looks like this if I use brackets to represent each individual section. So I have A in brackets, then I have A star. Like if I was writing code for this, I would have this, I'd figure out what's going on here, I'd apply the order of operations, I'd interpret it as this. And I'd say, okay, well, what have we got here? I've got A and B, and my basic building block for a single character looks like this. So there's A, and here's B. I mean, the nice thing is that you don't have to make it spatially fit out as a graph. So, sorry, there we go. It's like, okay, here's A, here's B. I know that my sort of star template, and like this is my input, this is my output. This is my input, and then this is my output. I know that the star template looks, or the clean star looks something like this. So this is my input, this is my output. And then it's like, okay, whatever goes immediately to the left of the clean star goes in this section here. So I would take my A and put that into there. But if this was like, A, B, C in brackets or something like that, then this would be A, B, C, and I'd take the whole thing and I'd put it in there. And then here's my input, and here's my output from the clean star. And then we have the OR operation and the B. So we have B by itself, which we evaluate out to be this. So then we have A star, we have B, and we connect them together with the OR template. We know that the OR template looks like my input, epsilon, and then you have the thing that goes on like the left of the OR. So the thing that goes on the left of the OR just here, the thing that goes on the right of the OR just here, and then they come back together over here with an epsilon. So I would put the A star in the top section, I would put the B star in the bottom section, and that would be the actual So for A star or B, this would be the actual epsilon NFA that I would generate out of that. So you can see there's like a whole bunch more states in there than we actually need. But the nice thing is the computer is doing that. I don't have to manually write out the DFA for this. We have a computer algorithm for evaluating this. So then if this is the initial state, we initialize the system as so, and then we can perform the greedy or lazy algorithm to evaluate this through and see what we end up with. And then you just do that, and you run that algorithm for each set of inputs as you receive each set of inputs.
So,
that's how I would approach it.
So I did a bunch of research. I haven't even started coding yet because I thought thinking is the main part of this whole assignment. So we got some predefined rules for epsilon NFAs. For example, A star, which is like I can write it out.
Yeah.
And then for A plus, then OR, which goes like two ways. So I was thinking, because they are predefined, can I just convert them into code, and then whatever inputs I'm getting from user, like A star and B, then I can usually use that predefined rules to add it, something like this. So May I show it on the code, please?
Like,
The one you just end up drawing it. Like this is how.
well, I mean, I wouldn't have a predefined rule for something like A star because there's no guarantee that you're going to get an A star
Yeah,
in the system. In theory, because the system supports brackets, you could get, because we said we could, you could potentially get something like A, B plus, C star,
Yeah.
something like this, which you're not going to be able to like predefine a template for like that whole expression.
Yeah. So I was like precedence rules, which is saying brackets first. I'll figure out the bracket first, which is A plus B. Then I got two of these. I'll do those, and then I got a star for it.
Mhm.
Then E is like it's coming. Either it's accept nothing or A plus C. Am I saying A plus C?
Sorry, what?
So I'm
So
sorry.
this is a B,
Oh, sorry. A B
AB plus C.
plus C.
Yeah.
Sorry. Is it alright if I use this one?
Yeah, absolutely. I don't have a marker, but if there's one floating around.
The green one?
No, these are permanent markers.
Oh.
Yeah.
Thank you. So A B plus C. This was the input, yeah. So first of all, inside bracket, which is A B plus.
Mm-hmm.
So they got my input. A B and this is plus, yeah. So A B followed by A B is plus followed by C and this is okay. Am I drawing it right? Because I need to see those. What I see on the internet is like they got predefined diagrams, which you just showed
Yeah.
us, which is like here it's going like this. And then this. So it's like this is what I meant by
Yep.
what I'm saying.
Yeah.
So this is for A star. A could be instead of A, I would write as X. It could be anything.
Yeah. Yeah. I mean, as long as you have,
As long as I
as long
have-
as you have it sort of set up where you go, okay,
Yeah.
well, this section in here
yeah,
is where I put whatever applies
Yeah.
the star
Yeah.
to. Yeah, absolutely, absolutely.
absolutely, yeah.
Yeah.
Was this a right diagram? I just
Uh,
A B.
that
followed by
is.
C and then star, which is star could be. Sorry, I think I'm missing something.
This is what is this? This is empty string or ABC.
Yeah. Because I'm not sure those.
Yeah,
those
this would
predefined
would
ones
be
are, like
that's literally no input
no,
or A
A,
followed
B,
by
C.
C or followed by C.
yeah. Okay, so I'm getting right.
Yeah.
Thank you.
Don't be afraid to go like super liberal with the epsilons, like just to glue everything together. It will probably make the construction of your graphs easier, even if you end up having like 100 epsilons in there.
Yeah.
if
so,
you- Yeah, I use them as glue. Just to, if I have these blocks,
so I just glue them together based on precedence rule, like star bracket, then star, then plus, then
Yeah.
union.
Yeah, if you end up with like 100 states in the system, it's not necessarily like a bad thing. It just means that it takes more computational power to evaluate all the epsilon closures, but that's not necessarily a bad thing.
Okay.
Yeah.
Awesome. Thanks.
No worries. Okay. Does anyone have any other questions? I'm not seeing anything in Piazza or in Echo 360 at the moment, aside from that one question about transition tables.
May I ask another question if nobody have?
Yeah, sure.
It might give a hint to other people, but I'm happy to give a hint.
Hmm.
How much like actually think it's like it kind of take a lot of effort
Hmm.
to find things. Say question. Okay. For example, I got A plus B plus C, and this is my diagram.
Mm-hmm.
Okay. This is how I'm thinking about to design my program. Is it okay to show it?
I'll probably end the recording there if we're
Okay, it's
gonna
alright. Then
dive into any
I'll
further
probably wait.
details.
I'll probably wait till 11 o'clock, rather than there might be
Oh,
some
no,
people who are gonna ask.
I mean,
questions.
if people want to ask any more questions, they've had an hour and a half to do so. So I'm going to pause the recording here. If anyone wants to ask any other questions, feel free to ask them now. But aside from that, wow, no, that's what we've just been doing. We'll catch you all next week, and good luck with your assignments. Keep asking questions on Piazza if you have them, and let me know if you have any other questions. I'll be keeping an eye out for them.